Okay, welcome to IA 215. Please forgive my terrible voice today. I'm a little under the weather, but today we're going to talk about rapid prototyping. And rapid prototyping has multiple cycles that it's going to run through. And the first cycle, let's see if I can see everything in my paper here. Is that going to work? Okay, there we are. This first cycle, I call it the paper prototype. In the paper prototype, the objectives are to just ensure you've got a reasonable layout, you get an estimate, you're going to get an estimate for cycle times. Now, an estimate based on the paper layout, it's not going to be real accurate, but it still gives you an idea of how to most efficiently lay out your components with your different robots, with your different inputs and outputs, and any other machines you need to include in this system. You'll figure out how to lay them out in a scale environment. I call it environment because it could be a scale drawing like AutoCAD, or you could do things in scale in PowerPoint even, or you could just do things on paper with scale sized little robots and machines and layout tables. So the paper prototype is the first cycle. We've already talked about that. Once you've looped through this cycle and move around these paper components until everything works well, then you're going to move on to the second cycle. I call this the human prototype. I've often said it to you guys. The second step is you want to do a physical layout to scale with props. So you don't need to do this with the real equipment. You need to do it with props, like a cardboard box or just a folding table, or, physical layout, measure it out, put tape down, and do a physical layout of your environment to scale. And then you are the robot. And then because you are the robot, then you might have your buddy time your movements between point A and point B. The purpose of this second one, like the purpose of that first cycle, was to make sure that all the pieces will fit together. Make sure that you've got a successfully designed environment where you're not going to have parts interfering with each other. The purpose of this human prototype is to find the 3D challenges. In other words, is there going to be an obstruction between 2 points, like the wall of a machine or a column, or the height differences will make moving up or moving down interesting? You're going to be looking for your gripper challenges. As you move your hand around, as you become that human prototype, your hand is going to have to duplicate what that gripper is going to do. And you'll find out very rapidly if you, by hand, have to pick up a part that is going to be extremely difficult for a gripper. So you're going to find gripper challenges. You're going to find also, you're going to get a more refined cycle time. Because you as a human pretty much run, not maybe a little bit slower, but you're not too much slower than some of these robots. You're going to be running at the same speed of all the mid-range robots. Now, of course, there are higher speed robots that will run way faster than a human. But for all the mid-range robots that we've got, the human prototype gives you a slightly better a cycle time, and it gives you an idea of how fast and how long it will take to run through each cycle. So the human prototype for me is cycle 2. Cycle 3 is the physical prototype. Apparently I can't type prototype. Cycle 3 is the physical prototype. Now, physical prototype doesn't mean that you need to go out and buy a robot. It can. If you have a robot, if you've got a training area with a robot, training area robot, then you can use that and do a physical prototype in the actual training area. But you don't necessarily need a robot on site at all. You also can find a vendor to help you. A lot of times you might call that vendor up and say, vendor, you're going to sell me this robot. I know you got one on your site for demonstration purposes. Can I come in and borrow it for a day with the table and some boxes, the same kind of setup that I used in my human layout, my human cycle, I can use in my physical prototype with the robot. So you might have a vendor that can help you out, or you might have an educational institution you can make a deal with and borrow one of their robots. So there's a lot of ways of making this work at no kind of without having capital outlay for $30,000 or $50,000 robot. All right. At this point, however, with the physical prototype, you need to have some sort of gripper. We're going to talk about 3D designing a gripper for a rapid prototype. You're also going to need you'll need parts to handle, and you'll need input and output. You need some way of inputting and outputting that robot. So you'll need to prototype or mock up some kind of input or output. If it's a tray, you'll need to 3D print a tray. If it's a manifold, you'll need to design a mock-up for the manifold so you can grab parts out of it. So you'll have to have some sort of mock-up for the prototype for input and output, the gripper and the parts. So all those are required with the physical prototype. Now, if you can 3D print these all, this is still relatively low cost. It's mostly just your time as a team member for this implementation. So this physical prototype then becomes the place where you really begin to sell. You verify absolutely cycle times, right? And you prove that it can work. And this is where you sell it to your bosses. You're going to sell it to your bosses. You're going to verify cycle times. You're going to sell it to your bosses. This is probably the most important to take a video of and to get out there and develop all that important, what do they call it, morale around this product. But we're not done yet. Do we want it to be complete system here? No, we don't want it complete, right? We want it to be hitting the minimum requirements needed to be successful to hit your metrics. Because after each prototype cycle, you're going to go through 3 phases for each one of these prototypes. So let me hit you the last prototype cycle before I dive into that. And the last prototype cycle is cycle 4. We'll call this the shop floor. Now, on the shop floor prototype, you can indeed use all the same fixtures that you already put together for your physical prototype that you had at your vendor site. You can use the same gripper, the same parts, the same input and output trays, everything. You could do that. It won't be necessarily the final gripper. Obviously, if you overstress a plastic gripper printed on a 3D printer, it's going to snap, and you probably want to go get one made up in steel, which you can actually get steel or other materials printed. There are shops that do that, like Shapeways. But the bottom line is, at this point, you could test the theory on the shop floor with your actual machines. Now, you might have to do a simplified machine interface. And why do I say that? Because simplified machine interface means that I don't necessarily write the code needed to interface with the software of a machine that I'll be working with as a robot. I might have the robot actually push a button with the end of the gripper, just as if an operator had pushed the button to start that machine or open and close the door. And that might be good enough to have in the prototype. Or I might mock up that interface to get a proof of concept before I spend money on the final interface that will be driven by software. It has to be written by somebody. But I can do a lot with machines that are designed to be run by a human. I can do a lot with a robot without having to write any kind of software to get that machine interface. Another important thing about this shop floor environment is you are going to be in the real conditions. So you want to see real parts. You're no longer going to be using your 3D printed sample parts or whatever the parts were that you used in your cycle 3 vendor site prototype. Now you're going to be using the real parts, and because you're going to be putting them into the machines and taking them out of the machines, actually machined, you're going to find out all of the real world conditions. The real world conditions are in, that includes dirt, dust, grit, shavings. All right, all of those things happen in the real world that you will now find out if are they going to affect your gripper? Are they going to affect how you fit into different fixtures? All of those things. So this is what we really want to pay attention to in the first shop floor prototype. And this cycle 4 isn't a one-off either. We're going to continually tune this as we run through cycles here. And then, of course, I don't talk about it, but once you've run through cycle 4, you improved your machine enough that you're consistently loading parts and taking out parts. If you're, for example, a machine loading application, then really the implementation is only a hair away from this. The final implementation might only be to do slight improvements to this shop floor prototype. In fact, the shop floor prototype may not be good enough to run unattended. For instance, you don't really rely on the plastic gripper you 3D printed, but it's certainly good enough to show you absolutely that this machine is capable of running and doing what we think it's going to do. So in each one of these cycles, we're going to do the same. We're going to do what's called a build, learn, adjust cycle. And in the build, learn, adjust cycle, we do our rapid prototyping. In each one of these, we do a build, learn, adjust. For instance, we talked about the paper prototype. The build in the paper prototype for us was to just use electronic version of paper. In my case, it was PowerPoint. to lay out the devices in PowerPoint, check the ranges, check for interference between the, say, the shell of the working machine and the robot mounting platform, and then try to test it. In other words, estimate cycle times and determine whether those cycle times are as quick as I need for my metrics. So the learning process is checking to see if we're hitting our target metrics. Don't go too far with this. In this rapid prototyping approach, we don't want to think about future maybe needs. We want to focus on what we know we need right now. You don't want to be distracted by tweaking things too much in each one of these phases. We want to just make it work and then move on. And of course, you want to check your parameters, like your cycle times, like your quality metrics, anything else that was a metric that drove you to decide to do this work cell, you're going to think about and check here in the learn. And then whatever you learn, you'll adjust. You might move around the input tray or the output tray. You say an interference problem and adjust something. And then you make the change and you test it again. Once you have achieved all your basic metrics, right, you stop. You say, all right, I've achieved my metric on this cycle, whether it's the paper cycle or the, you know, or the human cycle or the vendor prototype cycle or your learning area prototype cycle. You've proved that you've hit your metrics, and then you move on, each one of these. And some key learnings on this are minimum physical requirements. Always stick to the minimum physical requirements on the build. You want to do as cheap as possible. And I say cheap, I mean not expensive. But you don't want it to be sloppy. You don't want the materials you're using to be able to be kicked over easily or have their position bumped out of place easily. You want to have them locked in place firmly, but you want to use inexpensive materials to test all of your builds. Obviously, if it's electronic on the paper version, that's sort of a moot point. But it certainly becomes important once you start getting a real robot in place. All right? You want to go fast, better than perfect. You really don't want it to be perfect in any one of these build phases until you reach the very end. You want to utilize 3D printing as whenever possible, because when you're building these things using a 3D printer, you're going to save a lot of time and money. You can print a bunch of designs overnight. Well, that's not entirely true. I've had some guys, some women also fabricate their own prototyping components very quickly in their own wood shops. So it's not necessarily 3D printers the best. You can do very rapidly in some of your own wood shops as well. Next area in Learn, you want to test as much as possible with parts, users, and the environment the closer you get to the end of the prototype. You want to test target metrics only, and you can't be distracted by minor problems. Like if you have trouble dropping your finished part into your output tray, then you're going to move on during the learning process. And what you're going to do is you're going to adjust the design of your output tray so it's got more of a slant to the cavity. So when you drop the part in, it self-adjusts into that cavity, and then you'll retest it. You won't spend too much time fussing over the fact that it doesn't work. Just do your learning and move on. And that's true for any aspect of this prototype. Learn what you have to, make your adjustment, and move on as fast as possible. Now, the adjustment also, I would say adjustments, you should stick to 1 or 2 adjustments at a time before you build and retest. Don't do wholesale changes across the work cell. If you do that, then you might find yourself with a whole new set of problems, and you could find yourself chasing your tail on that. This is pretty much all I have on the prototyping process. After we reach the end of this prototyping process, you reach the end of cycle 4. You've done these build, learn, adjust until this is working right. Then you're going to be getting into the final design, and that's going to be the next lesson will be the final design of your automated work cell project. And where is my